all. Hope you're doing well today. Today we are talking about Chapter 1, the structure of muscular, nervous, and skeletal systems. Now I've broken this up into two different sections so that it's just easier, it's not so long, and so here we go. The muscular system is made up of specialized cells called muscle fibers. These cells are responsible for movement and are attached to bones or internal organs and blood vessels. Adult bodies typically have 206 bones and more than 600 muscles that are connected by ligaments, tendons, and soft tissues. The parts of the musculoskeletal system are bones. The bones of all shapes and sizes support your body. They protect your organs and tissues. They store calcium and fat and produce blood cells. The bone's hard outside shell surrounds a spongy center. The bones provide structure and form for your body. They work with muscles and tendons, ligaments, and other connective tissues to help you move. Cartilage is a type of connective tissue a cartilage that cushions bones inside your joints, along your spine and in your rib cage. Firm, rubbery cartilage protects bones from rubbing against each other. You also have cartilage in your nose, your ears, your pelvis, and your lungs. The joints are where bones come together, and these joints have a large range of motion, such as the ball and socket shoulder joint. Other joints, like the knee, allow bones to move back and forth but not rotate. Your muscles are made up of thousands of stretchy fibers. Your muscles allow you to move, sit upright, and stay still. Some muscles help you run, dance, and lift. You use others to write your name, fasten a button, talk, and swallow. The ligaments are made of tough collagen fibers. Ligaments connect your bones and help stabilize the joints, while tendons connect muscles to bones and are made up of fibrous tissue and collagen. Tendons are typically tough but not very stretchy. An inspection of skeletal muscle reveals collections of muscle fascicles surrounded by a layer of connective tissue termed the epimysium, which you see here in the picture. Each muscle fascicle represents a group of muscle fibers bound together by a layer of connective tissue termed the perimysium. Another layer of connective tissue termed the endomysium surrounds each individual myofiber. It's at the level of the myofiber where the basic contractile element of muscle, the sarcomere, is found. Now, muscle fibers are long and cylindrical in shape, and each fiber contains multiple nuclei, which are pushed to the periphery of the cell. When examined in cross-section, a typical muscle cell reveals between 4 and 6 nuclei, which lie just underneath the plasma membrane of the muscle fiber, the sarcolemma. Every millimeter of muscle fiber contains approximately 30 nuclei. In addition to the nuclei, other key structures that are specific to muscle cells within the sarcoplasm include the sarcoplasmic reticulum and the contractile apparatus made up of thick and thin filaments. Its principal function is to store and regulate the release of calcium, the key ion for initiation of contraction. The striated appearance results from a repeated pattern of protein deposition that makes up the functional unit of the muscle, the sarcomere. To fully appreciate the sarcomere, an electron microscope is needed to distinguish the ultrastructure of the cell. At this magnification, repeating series of light and dark bands are appreciated. The darkest of these bands is termed the Z-line, which serves as the anchoring point for the contractile elements and helps to mark the border of each sarcomere. Just inside each Z-line is a band that is lighter and broader, termed the I band. Named for its properties under polarizing light or isotropic, The I band is chiefly made up of actin, the principal protein of the so-called thin filament. Inside the I band is darker band termed the A band, anisotropic. This A band represents the actin containing thin filaments and myosin containing thick filaments, which are overlapping. Within each A band is a lighter region termed the H band, which has a dark line through the center termed the M band. The M band serves to cross-link the thick filaments. Briefly, when a motor neuron is depolarized, acetylcholine is released into the neuromuscular junction. Acetylcholine binds the nicotinic receptors on the surface of the skeletal muscles, leading to depolarization of the muscle cell. This depolarization causes the sarcoplasmic reticulum to release large stores of calcium. This calcium influx results in a conformational change that releases tropomyosin from actin. Actin is then free to cross-link with the myosin. In addition to this, the intracellular calcium activates the adenosine triphosphate, or ATP, in the myosin system, which powers the contraction. At an ultrastructural level, contraction results in a shortening of the H band. According to the sliding filament theory, which is what we've been talking about, a muscle fiber contracts when myosin filaments pull actin filaments closer together. This shortens the sarcomeres within a fiber. When all the sarcomeres in a muscle fiber are shortened, the fiber contracts. The theory has 5 stages. First is the resting. Then you have excitement and contraction, and then a recharge and a relaxation. So here's how it works. Again, the myosin binds to actin, and myosin changes its shape. It pulls on the actin filament, you see there in the bottom picture, or it reaches out and pulls on it, and the actin filament slides across the myosin filament. The theory also states that when calcium is released, it binds to a protein called troponin. This binding causes a shift in another chemical called tropomyosin. Tropomyosin is like a rope of molecules around the actin. Calcium then locates and binds with troponin, which pulls the tropomyosin out of the way of the binding site on the actin filament. Muscles move by shortening their length, pulling on tendons and moving bones closer together. Muscles can either contract or relax to cause movement. This movement can be voluntary, meaning the movement is made consciously, or involuntarily, done without conscious awareness. It is important to recognize that when stimulated, muscle fibers always attempt to shorten. The cross bridges attempt to pull actin towards the center of the sarcomere, which would cause shortening of the sarcomere and thus the muscle. Muscles are typically contracting against some type of external resistance, such as a barbell, which you see here in the video, or a dumbbell, which may be acting in opposition to the muscle force. If the amount of the force by a muscle is greater than the external resistance acting in the opposite direction, a concentric muscle action will occur, like as in a bicep curl. The resistance is overcome and the muscle shortens. If the amount of force produced by a muscle is less than an opposing external resistance, the muscle will lengthen even as it attempts to shorten. This lengthening muscle action is known as an eccentric muscle action. Now, what you'll find is that as a bicep is shortening, the tricep will be lengthening. So they work in opposition that way. If the muscle force is equal and opposite to that of an external resistance, an isometric or static muscle action results. The muscle neither shortens or lengthens but remains the same length. This would be in the case of a wall sit with the quads and the hamstrings working together, or even a plank. All muscle fibers contract and produce force, but they differ in their contractile performance and physiological characteristics. Muscle fibers from the same muscle may differ in the force they produce, the time they take to reach peak force, their preference for aerobic versus anaerobic metabolism, and fatigability. Muscle fibers can be classified into types based on different characteristics of interest. One biochemical property of muscle fibers is the ability to produce ATP aerobically, a characteristic called oxidative capacity. Since oxygen is necessary for aerobic metabolism, fibers that have large and numerous mitochondria and are surrounded by an ample supply of capillaries to deliver blood and oxygen are considered oxidative fibers. These fibers possess a large amount of myoglobin, which delivers oxygen from the muscle cell membrane to the mitochondria, enhancing aerobic capacity and lessening the reliance on anaerobic ATP production. Other considerations are maximal shortening velocity, maximal force production or specific tension, and fiber efficiency, which is the ability to produce more work with a given expenditure of ATP. Type 1 slow oxidative or slow twitch muscle fibers have high concentrations of mitochondria and myoglobin. Although they are smaller than the fast twitch fibers, they are surrounded by more capillaries and therefore they get more blood supply and oxygen. So that combination supports aerobic metabolism. They have high oxidative capacity and are fatigue resistant, particularly important for prolonged submaximal aerobic exercise activities. Type 1 fibers produce less force and are slower to produce maximal tension due to their lower myosin ATPase activity compared to type 2 fibers, but they're able to maintain longer-term contractions, which are key for stabilization and postural control. Fast twitch type 2 muscle fibers are further divided into type 2X and type 2A. Typically, these have lower concentrations of mitochondria, myoglobin, and capillaries compared to our slow twitch fibers, which means they're quicker to fatigue. These larger sized fibers are also produce a greater and quicker force, which is important in consideration for power activities. The type 2A fibers, also known as intermediate muscle fibers, are fast oxidative glycolytic and are a mix of type 1 and type 2X with comparable tension. Able to use both aerobic and anaerobic energy systems, these fibers have a higher oxidative capacity and fatigue more slowly than type 2X. So they're moderate oxidative and anaerobic capacity with some fatigue resistance versus type 2X, which are also known as type 2B fibers. These produce the most force, but are incredibly inefficient based on their high myosin ATPase activity, low oxidative capacity, and heavy reliance on anaerobic metabolism. They are fast glycolytic and therefore have a high anaerobic capacity and fatigue easy. So just kind of as an overview, type 1 or slow oxidative muscle fibers have high oxidative capacity and are fatigue resistant but contract and relax slowly. They are aerobic by nature. The two types of fast fiber types are known as type 2A, which is a fast oxidative glycolytic or FOG, and type 2X, which is fast glycolytic or FG fibers. Both are large and powerful with moderate to high anaerobic metabolic capacity. The FOG fibers have moderate oxidative and anaerobic capacity, providing them with some fatigue resistance in comparison with the purely anaerobic and highly fatigable FG fibers. So those type 1 muscle fibers are small, they're low and with slow force, and they fatigue slower than your fast twitch or type 2 muscle fibers. They are able to contract for a long period of time, and so they are fatigue resistant and really important for aerobic activities, stabilization, and postural control. The type 2 muscle fibers are large muscle fibers. They're greater and quicker at producing force, and they fatigue faster than the slow twitch type 1. There's the two types. So type 2X produces the most force, but it's really inefficient and fatigues very quickly within 3 to 6 seconds. Your type 2A is a mix of type 1 and type 2X muscle fibers, so it fatigues slower and produces more of short-term contractions and supports your power activities. This chart does a great job of summarizing all of that, looking at the mitochondria, the capillaries, and all of that with the types of activities that are associated with the muscle fiber type. Now, having said all of that, fiber types are not discrete categories. These characteristics lie on a continuum rather than being discrete categories. Adaptations will occur due to physiological stressors such as training. Muscles of the body differ in their fiber type distribution, such as the soleus, which has a high composition of type 1 fibers, versus the quadriceps, which is a mixture of type 1 and type 2 muscle fibers. You and your muscles are not comprised of one type of muscle fiber. All of your muscles are a mix of fast twitch and slow twitch muscle fiber types. Whether you have more of type 1 or type 2 depends on your activity level and your age. So non-athletic individuals have close to a 50-50 balance of fiber types. When you start looking at highly skilled, top performing athletes, some differences may begin to appear. Power athletes have a higher ratio of fast twitch fibers, with sprinters having about 70 to 75% type 2. Whereas for endurance athletes, they have more slow twitch fibers. Marathon and distance runners are going to have more like 70 to 80% of type 1 muscle fibers. Of course, muscle fiber type is not the only factor in an athlete's success. There are plenty of other factors that take an athlete from good to great. Age is also a factor for our muscle fibers. It's probably the biggest factor, to be honest. Aging causes a loss in lean muscle mass with a decline in our fast twitch fibers, mostly because we don't train them, but especially that type 2X. But there's also an increase in our slow twitch fibers. Recall that the fast twitch fibers are larger in size than the slow twitch and are metabolically efficient fibers. Thus, loss of lean muscle mass can contribute to age-related metabolic dysfunctions, body composition changes, even an increased risk of falls. Resistance training can combat that decline. You can modify fiber types through exercise. Your type 1 muscle fibers can be developed through endurance training, such as low resistance, high repetition, or long duration and low intensity. Your type 2 muscle fibers can be developed through strength training. Resistance training increases the size of both type 1 and type 2 muscle fibers. There's greater growth or hypertrophy that occurs in type 2 fibers and increases actin and myosin filaments. This results in an increased ability to generate force. Your fast twitch fibers can also recruit slow twitch fibers. So endurance training at high intensity intervals can be effective in improving aerobic power. Tapering during your training programs, such as reducing volume and intensity, can also improve the strength and power of type 2A fibers without decreasing type 1 performance. One study investigated muscle fiber changes in recreational runners training for a marathon. After 13 weeks of increasing mileage and a 3-week tapering cycle, not only did the functions of type 1 and type 2A fibers improve, but type 2A continued to improve significantly during the tapering cycle. And this is just another example of a chart where it's depicting muscle fiber type and their use during certain physical activities. And so you can see with walking, type 1 is typically the muscle that you're going to be using, the type of muscle that you're going to be using versus type 2. On the other hand, with volleyball, you can see you're not using very much type 1 muscle fibers. It's more of type 2 muscle fibers. That ends our discussion today. We'll pick up in part 2 of chapter 1, where we'll be talking about the nervous and skeletal system. I look forward to talking with you again. Have a great day.